You're not gonna believe this. I got shocked on the way in.
No way. Did you get struck by lightning?
Well, that's the weird thing. I just touched the elevator button.
Oh. Well, the elevator button is made of metal and is therefore a very good conductor. You're probably carrying excess negative charge.
What? How does that happen?
Some objects, like the metal in the elevator button, are better at conducting electricity. And if you had touched like the wall, for example, which is like an insulator, you probably wouldn't have been shocked.
Tell me more.
Well, there are three classes of materials: conductors, semiconductors, and insulators. Conductors are often like metals, like silver, copper, nickel, and they're very good at moving charged particles over large distances. I think it's because they have a lot of free charges. Like, insulators don't have charges like that, which makes them bad at conducting. Semiconductors are somewhere in between. Well, let me find a video that has more information.
The difference between insulators and conductors. Conductors are very good at moving charged particles because they have what are called valence electrons, which are electrons that are functionally unbound from the nucleus of their atoms. These atoms form a crystal structure called a lattice, through which these unbound electrons move freely. This flow of free charges is sometimes described as a sea of electrons. Insulators, on the other hand, inhibit the flow of electrons because of the strong bond between the host atoms and their outermost electrons. Due to this effect, materials like wood, glass, and rubber act as buffers to the flow of free charges. Understanding these principles is crucial to the functioning of everyday objects such as electrical cables, in which we find lengths of copper wire that conduct electrical flow that are encased in an insulating rubber coating which guides the current.
That's interesting. But let me just make sure I understand. So in the case of a conductor, free electrons added to the surface will be redistributed throughout the material in accordance with the laws of thermodynamics. Whereas in the case of an insulator, the electrons will remain fixed where they were placed, ready to discharge at a moment's notice.
Oh, so that's how the polarization of a plastic rod must work.
What now?
Like polarization. Polarization occurs when a charged object induces separation in an insulator. This separation occurs at a molecular level, where the electric field distorts the negative cloud of electrons in the opposite direction of the electric field. This results in an attractive force between the two.
That's very interesting. But I wonder if this has any real-life applications.
Let's see if I can type it into YouTube and see what pops up.
What happens to insulators? On a different note, it's because of this property of the atoms of non-conductive substances, such as the rubber in a party balloon, that we can induce a dipole, or in other words, polarize an insulator. This polarization is admittedly weak, but it's enough to stick a balloon to a wall. When the balloon is rubbed against the hair, excess electrons are deposited on the surface of the rubber. Because the rubber is an insulator, the electrons do not redistribute throughout the rubber, and instead remain at the surface where they were placed, charging this part of the balloon negatively. When the balloon approaches the wall, which is also an insulator, the excess charge on the rubber polarizes the charge at the surface of the drywall. Consequently, you have a negative charge on the balloon that is attracted to the induced positive charge on the wall, which generates an adhesive force strong enough to overcome the force of gravity and keep the balloon against the wall.
See, with you around, I didn't even have to go to the lecture.
What about the participation credit?
What participation credit?